In these next few pages, we're going to associate the idea of limits and the idea of continuity, which we have recently introduced, and tie a connection between them. Remembering that a function is continuous if it can be drawn as a single pen stroke, how does that get represented when it comes to formulas and more abstract conditions? Here's the definition that mathematicians have come up with. A function is continuous at a point if the function is defined at the point. So that's the first criteria. And I'm going to emphasize the at part there. When we plug in the number c into our function, we get something finite back. And also, the limit as x approaches c of f of x is also defined. And so the function has a trend, and trend to a finite number as x approaches c. So nearby that point, the function's well behaved, and as the final piece, both of these values are equal, the limit and the function value itself. So at x equals c and as x approaches c. Both of those values with the function will be identical. And what we say is a function is continuous on an interval, ab, if it's continuous at all the points on the interval. So this is for a single point, but if we keep seeing the same pattern that the function values and limits agree consistently, then we can spread that out over a longer interval. And again, just for an example, if we had y equals x squared, if we consider that graph, again, we know from the graph and the intuition about continuity that we can draw it as one pen stroke, so very clearly it is continuous under that test. But also if we pick any other point on the graph, call that c, when we approach that x-coordinate on our function, we end up heading towards this dot where we actually would be. And likewise, if we approach from the other side, the function is getting closer and closer to the value at whatever c is there. That would be c squared. So there's no discrepancy between where we would end up if we just followed the graph without going to a point and the point on the graph itself. That is the technical definition of continuity. So how can we use this to describe some of the situations we've seen earlier? Well, we looked at the graph of y equals sine of x over x. And remember, that looked roughly like this. It was a curve that went up to almost 1 and then kept going. Well, the first problem we have there, let's actually go down the conditions. We say it's not continuous at x equals 0. Why not? Because f of 0 is undefined. We can't plug in 0 into this formula and get a number back. That's why we had the open hole in our graph. And so right away we've lost that first condition required for continuity. The function is not defined. But the limit as x goes to 0 of f of x is defined, but too late. Too late for continuity. If our question is about the continuity of this function, then by not having the function defined there, we already have a hole. There's no way the function can be continuous. So flipping back for a page for a second, we already rule out that function sine x over x being continuous because it lacks a definition at the point x equals 0. This could be true. We also wouldn't get an equality between the two values because one of them doesn't exist. So we could go further. But it's enough to not satisfy one of those three conditions to not have continuity. To have continuity, you need all three. All right, so that's how we can explore the continuity question of a point like this. Another thing we can do, and we're going to do this a lot, quite frankly, when it comes to studying limits, is let's take a look at the limit as x goes to 4 of x squared plus x minus 3. So this is simply a quadratic polynomial. And we know that polynomials are continuous everywhere. Every polynomial can be drawn as a single pen stroke. Well, what that means is that, of course, this particular example is going to be continuous. It'll be continuous everywhere, but most importantly for this question, it'll be continuous at x approaches 4. Or sorry, it's continuous at x equals 4. And there, from the third condition of continuity, the limit as x goes to 4 of x squared plus x minus 3 is going to equal f of 4. In other words, where we're going to end up if we follow the graph closer and closer and closer to 4 just happens to be the exact value if we plugged in 4. That's what this value here means. Plug in x equals 4. And if that's the case, then we can simply plug in the values here. We can skip this step when we write it on paper. But we say this function is continuous, so as x approaches 4, we're going to end up exactly where we would go if we just plugged in x equals 4, which would be 16 plus 4 minus 3, or y equals 17. So continuity can help us answer these kinds of quick and easy limits. Can I sub it in? Is the function continuous at that point? If it is, then we just plug in the value of the limit, and they will be the same because of that continuity definition. Last but not least, let's take a look at an example of a graph with a hole in it, but where the hole has been filled in. So this is the graph we saw earlier where the function increases, increases, increases. Then there's a gap in the straight line, or the continuous line here. At x equals 2, the function jumps up to y equals 6. And what we'd say with this is that f of 2 is equal to 6. When we plug in 2 exactly, we get 6. We also have that the limit as x approaches 2 of this function, well, that's going to be what would happen if we were just following the curve closer and closer and closer. Where would we have ended up? Well, that would be at x equals 4. Sorry, at y equals 4. So as x gets closer to 2, the y values approach 4. So both f of 2 and limit as x goes to 2 of f of x exist, but they are not equal. And as soon as we say that, then we've lost our continuity. So just as we can see in the graph, there's clearly a break that shows up in the algebra and the conditions for the function itself by comparing the limit value, which is 4, to the function value, which is 6, at and around the point here. And so we'd say here the function is not continuous. That was our third condition, that the limit and the function value be the same, and so our function is not continuous at x equals 2. So in terms of our statements here, there is our continuity statement. The function is not continuous at x equals 2, but the limit, absolutely, which is a part of the continuity definition, but not the whole thing. The limit there exists and it's fine. It's a nice limit. It just doesn't happen to line up with the value of the function itself. And so one of the challenges, of course, is just to keep straight what does it mean when we say the limit exists? Well, it means that the function is heading towards something finite, a single finite value. What do we mean when we say a function is continuous? It means that we can draw it as one unbroken curve. In this case here, we cannot do that, so it's not continuous, but the limit does exist. So just keep those two ideas distinct in your mind.